Yeah. Like, it's 12:30. Oh my God. And you must get so much done. No, I'm 54 hours. I'm sure you ran.
So we are going to go ahead and start our calculator FRQ packets, which there will be a test next Friday. But just want to kind of highlight a few things here. First, if you can turn to page 21 in the current packet, just want to highlight formulas that you want to make sure you know for tomorrow's test. So this is on the previous, the 4345 packet, this one here. There's no summation formulas that you have to worry about. We just have to obviously know power rule for derivatives. The idea is that if you have these 6 derivative rules written at the top of your test, then you can also use these to arrive at the trig integral rules. Okay. Power rule for integrals, first theorem, which is just basically applying that definite integrals. You're going to take the antiderivative, then plug in upper bound minus lower bound. Second theorem. And then also the variation for second theorem, which I didn't put on the formula sheet. So if you want to write it down as well, this is the variation. Which is this. It's basically the same thing as the first theorem. It's just that if the lower bound is also a variable, we have to do the same thing that we did with the upper bound. So f of p of x times p prime minus f of q of x times q prime. So you can put that on your formula sheet as well, just as a reminder for you to work on memorizing those. Okay, so trig integrals, we've been working on that, but we know they're just the same, essentially the same as your derivative rules, just working backwards. And then also average value theorem. Here, what I boxed off here, actually, it should include this as well. This is what we're going to be kind of working on today. So we're going to be seeing some of these formulas, but this is going to be for the calculator portion that you're going to have to know. So you can box that off and know that you don't have to worry about these variations of first theorem for tomorrow's test. Also, at the end of class or near the end of class, I do want to run through definite integral problem involving trig, where you have to make sure you know your unit circle values. And then maybe I'll do another even and odd function. But you know, yesterday, I think we pretty much were able to hit every type of problem. Okay, any questions about the test for tomorrow? Okay, so you're going to need your calculator, and we're going to work first page, and if we can also get to the second page, that would be great, of our new packet. Yeah. Use this one. So the graphing calculator is preferred, but if you have the 36 Pro, it can do a lot of the calculus process as well. It's just when we get to the graphing, this becomes a little bit more difficult to use because obviously you can't create graphs, but you can find ordered pairs. I mean, there are workarounds with this, but graphing calculator can do things a little faster for us. But that's only with the graphing. But I'll show you what the calculator can do for us. So the big features is that our calculator can find a derivative at a point and can also find definite integrals for us. We need to be, so on the calculator portion of the FRQ of the AP exam, we need to be able to know how to arrive at those values. So let's look at number 1 here. It says a particle moves along the y-axis. So the graph, this particle is either moving vertical up or down, or it's motionless. So there's only a couple of things that it can do. So a particle moves along the y-axis with velocity given by v of t. So this is already the velocity function, v sine of t squared. In which direction, up or down, is the particle moving at t equals 1.5? So if I want to find movement, I'm going to be sticking with velocity. So there's no need for us to find the derivative. We're already at the velocity function. So we're simply going to plug 1.5 into our velocity function. So you can just plug directly into your calculator 1.5 sine of 1.5 squared and make sure that you're in radian mode. Okay, we're always going to be in radian mode for this course. So you can double check. If you go to mode, you should be able to see RAD highlighted and not degree. Or on your graphing calculator, you'll see radian under mode. So obviously you can just plug this in here, 1.5 sine of 1.5 squared, 1.167. That's obviously greater than 0. So if I get a positive velocity, I know my particle is moving up. Right. This problem establishes that this particle is moving up or down. So that means up is positive and down would be indicated by a negative velocity. Something else that I think could be of use, especially down the line, is where we don't have to, where we prefer not to plug in the same expression every time by hand, especially if we have something that can store that function. So I just want to kind of begin to show you what that could look like. It's kind of hard to do on the 36 Pro, but on the graphing calculator you can. So if you go to y equals, and if you type in x sine of x squared, and by the way, if you ever want to use your calculator, always use the variable x. Okay, don't try to force it into a different variable. It'll start complaining. So on paper, you're going to copy whatever variable that they have, but then in your calculator, you're going to use x. So go to y1, go to y equals, and you can type in x sine x squared. Go back to your home screen, so second mode. And then if you have this feature here, see. If you go to alpha trace, so I'll put this on the board, but alpha trace, once you're at your home screen, so to get to your home screen, you'll do second mode to get to your home screen. If you do alpha trace, you should see a Y1 pop up. And you can scroll down to any of the Y functions. And then you can have Y1 show up. So now we're calling that function that we just entered in. And if you do parentheses 1.5, it's going to plug that value in. It's not a big deal if it's not any faster if it's just a simple expression. But if it's a more complicated expression and you're having to call it over and over again, rather than having to type it in every time, you can just make it. So another way you can do it is you can do vars, yvars, function, y1. So I'll put those both options on the board. So alpha trace can help you get to that menu to call the function that you want to call. But you want to do this at your home screen. Okay, part B, find the acceleration of the particle at time t equals 1.5. Is the velocity increasing at t equals 1.5? So acceleration is the what of velocity? Derivative, right? I mean, we could find a derivative. This is manageable. We can go through product rule and chain rule, f prime g plus f g prime. But this is calculator section. We're going to make the calculator find the derivative at the point for us. So up there on the board, I have those two major features you're going to see. Math 8 is for your derivative. Math 9 is for your integral. So let me show on the graphing calculator first. If you do Math 8, and if you're using an older calculator, one that I have there, then I have some instructions on the key, which I can walk with you later, and I can also put it on the board. But let me show what most of us have. So if you do math, you can either hit Math 8 or you can, so math is on that first column there. And then you can either scroll down to 8 or just type in the number 8. You see that n deriv. So we're going to say d over dx. And you can type in that function x sine x squared. Or you can do alpha trace and just call that y1 that is holding that function. And then you can do x equals 1.5. So this is doing a couple things for us. This is finding the derivative of this function and is plugging in and finding the slope or finding the value of the derivative. So I'm plugging in the velocity, asking to find the derivative of that, which is acceleration, and it's going to plug in that 1.5 into the acceleration. So it's doing a lot of things for us. So this is your acceleration value. We will get the same value if we were to go through product rule, f prime g plus f g prime, build the derivative, get to the acceleration, and then replace every t with 1.5. We would get the same value. So basically, this is acceleration. So let me write this down, and I'll show you on the 36 Pro. So v prime of 1.5, which we can also call a of 1.5, is equal to negative 2.0487. Now, on the AP exam, you can either truncate, you can either drop that fourth number there and just do 3 decimal places, or you can make that third digit round to 9. So you have some options on the AP exam. You can either write it as negative 2.048, or you can write it as negative 2.049. And there's no units of measure provided. And we know that this is less than 0. This is negative velocity, so therefore velocity is decreasing. So a lot of the keystrokes on the calculator, I'll probably just leave those instructions on the board, just so that you have access to it and you're not having to kind of allow those skills to eventually, eventually memorize it in time for the AP exam once we get enough practice. But on the test, I will put those keystrokes on the board so that you're not having to feel like you got to memorize all those steps. Now on the 36 Pro here, there is a a derivative notation. Do you see how there's that d over dx there under in that blue above the ln? So if you do second ln, you're going to see a very similar notation. So here you can type in x sine x squared, which is your, and then your x is down here next to your 4. So x sine x squared. And then you can establish 1.5. So this will do the same thing. This will plug in that 1.5 into the derivative that we of the function that we see there, and it'll give us same thing. Okay, part C, given that y of t is the position of the particle and y of 0 equals 3, find y of 2. Now, we don't have our y function in front of us. All we have is velocity right now. But if we rearrange first theorem, we can actually create a situation where it's beneficial for our particle motion problem. So here's the formula. The formula is any, let's see, how do I write it on my, yeah. And this is in this variation formula here, which I will specify later. So the idea is that any position I'm looking for, any final position I'm looking for, I'm going to have an anchor point, my initial position, that's my given position, plus my displacement, how much progress, how much movement I've made since that starting point. So if I'm looking for where's this object going to end up, you're going to start off with the location that the problem gives you, and then you're going to add the progress that the object's going to make in that time interval. So here's the formula. Y of b is equal to y of a plus the integral from a to b of y prime dt. There's tons of different variations of this, but basically it's following this form. I'm going to use up some of the space for part D because part D won't need a lot of space. So if I want to find y of 2, if I want to find my final destination of y of 2, I need to have a starting location, which is y of 0. And then I want to know how much progress have I made between 0 and 2. So I'm going to find my displacement between 0 and 2 for my velocity function. So this will tell me how much progress I've made since my starting point. And if I can figure out where I start plus how much movement I'm going to make, I'm going to know where I'm going to end up. So y of 2 is equal to, we know y of 0 is 3. So we're starting at y-intercept 3. And then we're going to have this much movement. So to do this, we could go through use substitution, take the integral, but we're going to make the calculator do it for us. So there's the other feature on the board there, Math 9. So if you go to Math 9 in your calculator, FN integral. And then you're going to see that integral notation show up, that math print notation. If you don't have this math print notation, I'll show you later how to enter that in. But most of us have this. So you're just going to copy exactly what this is saying from 0 to 2. So lower bound 0, upper bound 2. And then in this function, you can type in x sine x squared, or you can call that y1 that was holding your velocity function. So do alpha trace y1 dx. So that 0.8268 tells us that this object, this particle, is going to move up 0.828 units in that between those two time periods. So if we know that it's going to move up 0.828 units, that means if we start at 3 and if we move up 0.828, we're going to end up at 3.828 on the y-axis. On your 36 Pro, if you're using that, there is that option there right below your d over dx. Under this x exponent there, you see that integral notation in blue. If you do second e, you're going to see that notation, and you can type in exactly what we just talked about. So you go from 0 to 2. In this case, you may have to just type in that function as you see it. Always use the variable x, though. So x sine x squared. Okay, any questions so far? Part D, find the total distance. So total distance has a specific formula. Total distance is basically involving absolute value. So total distance is just the definite integral from a to b of the absolute value of v of t dt. Right. There is no starting point to add. It is just basically your displacement with the absolute value bar around your velocity function. So for our problem, it'll look like this. Integral from 0 to 2, absolute value of, in this case, v of t, which we can type in our calculator. Make sure your absolute value bar is only going around your velocity and not around the full integral. So again, go to Math 9. Go from 0 to 2. And then if you do math number ABS, you're going to see that absolute value bar. Math num ABS. Put on the board. And then you can type in your velocity function inside, or if you want to call the velocity function that you store under y1, you'll do alpha trace y1 and dx. It may take a second. On your 36 Pro, you'll do second e, which will get that integral notation from 0 to 2, and then math. Yeah, same menu, math number ABS, math num ABS. Okay, 1.173 is the distance, total distance. So just with this one problem, we're able to see basically the new calculator skills that you may not have seen in the past. But a lot of the other ones that we're going to use are ones that you saw in AP Pre-Calc, which is graphing and finding intersections and finding x-intercepts. So, but really, it's just these are really the only additional things that is new with your calculator that you need for the AP exam. Getting to n deriv, getting to f an integral, getting to absolute value. There's not much more to it than that. Okay, but we still need a lot of practice. We still need some practice to eventually get ready for that. Okay, any questions? Okay, next up. The temperature in degrees Celsius of the water in a pond is a differentiable function. So differentiable function just means a smooth curve There's no sharp turns, there's no holes, there's no asymptote. Use the data from the, okay, so this is what this table is showing us. It's showing us that at day 0, temperature is measured to be 20 degrees Celsius. 3 days later, they measure the temperature again, 31 degrees. Day 6, they measured again, 28 degrees. Day 9 is 24 degrees. Day 12 is 22 degrees. And day 15 is 21 degrees. So you see that it's fluctuating basically between 20 and 28 degrees, or 28, 38, 31 degrees. Okay, use the data to find an approximation for y w prime of 12. So if we want to find an approximation of w prime of 12, we know w prime is related to derivative. What's another word for derivative? Just what? Slope. Yeah. So how do we find slope given order pairs here? Find 2 points, right? So what points would you use if you want to find the rate of change on the 12th day? Which order pairs would you choose? Any guesses? Like, there's multiple right answers. Would we want to choose order pairs like 0 and 3? What would be a better? Yeah, so basically anything around your target, right? This is only an approximation. So you can either choose 9 and 12, you can either choose 12 and 15. You can either even make an argument for 9 and 15. But as soon as you start picking order pairs away from your target, then your accuracy is going to be, is not as strong. So any order pair around this is fine, especially if the number that you're looking for is showing up. Now, if it's asking for w prime of 11, then what order pair should we definitely use? Yeah, just use 9 and 12, right? Because 11 is clearly between 9 and 12. We definitely want to use these. We don't want to use anything else. But if we're landing directly on 12, then you can make an argument, okay, maybe 9 and 12, maybe 12 and 15. But I'm going to choose 15 and 12. Their answers are going to be slightly different, but on the AP exam, this would be, all would be acceptable. So slope is just change in temperature over the change in time. So 21 minus 22 over 15 minus 12. So -1 over 3. What's our unit of measure going to be if we're talking about rate of change? This is -1/3 what? Degrees Celsius. What does the 15 minus 12 represent? Per day, right? It's a rate. So our units is also going to represent kind of that slope feel to it. So this tells us that on the 12th day, the temperature is decreasing by a rate of 1/3 degrees Celsius per day, approximately. Okay, so part B, approximate the average temperature. So average temperature, that's basically average value theorem, of the temperature using trapezoid approximation between 0 and 15. I'm going to adjust this here. Let's say between, just so that we can save a little bit of time. Let's say it's between 0 and 12 days using length of delta t 6 days. So we're just going to create two subintervals here. So 6 days, so from 0 to 6, and then from 6 to 12. So average value, average temperature, we're going to use the formula 1 over b minus a, integral from a to b of w of t dt. My a and b values, I'll use 0 and 12. But we're not going to have a formula to plug in. We're going to use trapezoids to approximate this region using the table of values. So we'll do two trapezoids. We know that trapezoid's area is 1/2 width, height 1 plus height 2. So I'm just going to take care of the integral portion here. So my width is 6. And then my height, I'm just going to use where the bars are pointing down, right? So 20 and 28. So 1/2 width, height 1 plus height 2. And then again, 1/2 width, height 1 plus height 2, 28 plus 22. We're going to add all that up, but we still got to divide by 12. And then we should be expecting something in the range of between 20 and 31, right? If we get our average temperature to be like 50 degrees, that doesn't make sense, right? Something doesn't go quite right. We know it's got to be somewhere between 20 and 31 because 20 is the lowest and 31 is the highest. We can't have an average temperature that's below 20 or above 31, right? That wouldn't make sense. So we're just going to add these numbers up. So 294, we can't just leave it in this answer, right? It doesn't make sense. If temperature is between 20 and 30, it shouldn't be, the average temperature shouldn't be 294. We got to make sure we divide by 12. 24.5, that feels more reasonable, right? So these are the approximation methods. And then these problems are revisiting these scenarios, but then from a calculus perspective, where we can actually use the integral and the derivative feature. We actually have a model rather than a table of values that can give us a better idea how the temperature is changing at every moment in time instead of just 3-day intervals. So let's pick this up on Monday. Okay. I'd like to spend some time just to do some more review for tomorrow's test. So Monday, we'll have a full day to do test review. Tuesday, Wednesday, Thursday, we need to start our next unit, but I'm going to steal some of those times at the end of class just to continue reviewing and getting us ready for the 3 FRQs we're going to see next Friday. All right, so if you guys can get out a sheet of paper here, I have some problems that I created for us to try. So you just find any open space in your notes, or if you want to grab a spreadsheet, or if you have some note paper. Write this down. Okay, so if we're looking at this problem, we know that we don't have a single integral rule that can match that much going on, right? So if we don't have a rule that can match what we see in front of us, we know we got to do use substitution. If we want to use substitution, we would prefer to see some parentheses. How can we get some parentheses to show up? Write this as what? Where can we put these exponents? Yeah, outside a set of parentheses, right? So now we are dealing with two parentheses, so we're going to have to decide which is a better fit for our u value, right? We have two options here. Only one of them is going to end up working out. Either our u value is cosecant of x, or our u value is cotangent of x. And if you're trying to decide between those two, think about the derivatives that's going to be produced out of each of them. Let's consider cosecant first. If the derivative of, what's the derivative of cosecant? Negative cosecant cotangent. Do you see a negative cosecant cotangent elsewhere in the problem? No, right? So that is probably not going to be a good fit for us. So what if our u value was cotangent? What's the derivative of cotangent? Cosecant squared, right? I mean, there's a negative there, but we see for the most part something to so that our derivative is going to show up elsewhere in the problem. Right? That's a better fit. So if you can kind of look ahead to see, okay, if I'm deciding between two u values, think about the derivative, and then think about when you look at the derivative of your potential u value, do you see a version of that somewhere else? If you do see that, chances are that's going to be a good fit for your problem. Okay, so our u value is going to be cotangent of x. Derivative is negative cosecant squared x. Cross multiply. Solve for dx. And then your initial goal is to just find a replacement for those underlined portions. Everything else you're going to rewrite back into your problem. Just like what we expected, the x's cancels out nicely. We know that we're on the right track there. Make sure you keep track of your negative. But then once you pull the negative out, everything is nice and clean. We have a power rule available for us. We're now ready to apply a power rule. U cubed becomes u to the 4th over 4. We have bounds involved. Are we ready to plug in the bounds at this time? Can I do half bracket and start plugging in the pi over 3 and pi over 6? What's the issue? These bounds are in terms of what? Which variable? These are in terms of what? X. But this is in terms of u. So we have to figure out, you have to understand that I can't plug x into u, then the answer I'm getting is not correct. So either you convert these bounds in terms of u, you can do that through cotangent of x, or this is what I think most of us prefer, bring this back in terms of x first, and then work in those upper and lower bounds. Okay. Upper bound gets evaluated first. Followed by lower bound. All right, can we leave our answer like this? Yeah, we got to keep going, right? You have to use unit circle values. You can't stop until you get everything down to numeric values. Once it's down to numeric values, then you can leave your answer and simplify it, and that's fine. But we got to think about, okay, what's cotangent to the power over 3? What's cotangent to the power over 6? So here are the order pairs for your pi over 3 and pi over 6. You know cotangent is x over y. So cotangent of pi over 3, which is the 1 over root 3. Cotangent of pi over 6, which is the root 3 over 1. Now I can leave your answer alone. That's okay. You don't have to clean that up. But if you see any trig in your answer, that's not far enough. We got to go one step further. All right, let's do even and odd problems. See if you guys have any questions about those types. Okay, write this down. Try this one here. Okay, so our strategy is start with the shorter interval, right? Which interval do we want to start with? Start with this one, right? But is there anything that we need to adjust with this integral? What do you notice? Sorry? Yes, overlaps the other one, but in terms of graphing this, can we go ahead and start graphing or something a little off? Yeah, the 2 is not really showing what it's really doing because the bounds are out of order. So if we're going backwards, that 2 is not really a 2. So what can we do to make it more straightforward? Switch the bounds. But if I switch the bounds, what's really happening? The 2 is really what? Really -2. So these are the same things, but it's easier for us to see, okay, this is obviously below the x-axis versus, this is not so obvious that this is below the x-axis. So if we're reading backwards, 2 would mean the same thing as -2 reading forwards. So after we make the adjustments, we can now graph. Sorry, below the x-axis. All right, so now that we have this on our paper, it's an even function. What can we do on the other side? Also what? Also a -2, right? Even function, we can create equal, but we can create mirror image on the other side. Now we can focus on the larger interval. From -4 to 8 equals 7. Don't create a big overlap. You know that these are already set in stone. We don't want to be changing or adding to this region here. This region is already set. We just want to figure out. We just know that these regions will add up to be 7. Well, I have -4 showing. What can I add here so that everything will add up to be a +7? Right? 11 minus 4 is 7. If this is 11, you know that this is also 11. Now that you have your full graph in front of you, now you can add the region they're asking you to add from 0 to 8. Okay, so make sure that you know exactly what you can expect on the test tomorrow. Tomorrow morning help session. I do have another review worksheet. It doesn't have everything on it, but it has a good number of these topics. If you want to pick one up, you can pick one up. But tomorrow I'll be working on going through page 17, 18 in your review packet, in your 4, 3, 4, 5 packet. All right, come hit your phones. Okay. Listen, you guys. Yeah, thank you.
Sorry for wondering. This was yesterday's.
Okay.
And then page 3, right? Completely done with pages 1 through 8, but I have an annoying pictures I can show you. It completed.
Okay. Yeah, thank you.
That was been homework for the last 2 days.
Yeah, me too. So.
Well, I haven't looked back.
Yeah, I'm saying.
I could play with that.
Okay, yeah, I saw it. Thank you. All right, stay for your test. See you tomorrow.